dear colleagues, if there's somebody from organizers to maybe in the main hall, to say that we can start.
I think we can start the next session.
Yes, thank you. So my name is Irina Lamazova, and I'll moderate this section on formal methods. And we have 3 talks. We have 20 minutes for each talk, and so including questions. So I'll ask speakers to have it in mind. Yes, and then so just our first talk is mechanized theory of event structures, a case of parallel register machine. And I guess that the speaker is in the main hall, so just he's offline. I do not see the speaker in the list. Oh, yes, thank you. I see slides. So the authors of this talk are Vladimir Gladstein, Dmitry Mikhailovsky, Evgeny Moiseyenko, and Anton Trunov from St. Petersburg University. And the speaker is Vladimir Gladstein. So.
Yes, I'm going to present this presentation with Dmitry Mikhailovsky.
Yeah,
so, okay, let's start. So let us consider an example. Here we can see a program consisting of 3 concurrent writes to a shared variable x, and then we read from this variable. So traditional operational interleaving semantics assigns to this program 3 factorial, that's 6 traces and 24 events. That is all interleavings of individual instructions. As one can see, such encoding is quite excessive, as the number of traces grows very quickly with the size of the program. But fortunately, we can encode the semantics using a single event structure consisting of 6 events in total. So the event structure consists of a set of events and the 2 relations. In our case, events are atomic read from shared memory or writes to memory. So the first relation is a causality relation. It is a partial order. It reflects the causal relationship between atomic events of computation. So let's consider this graph. Here you can see that that each read connected with each write. Yes, for example, this read connected with this write like this, with this write like this, and with this write too. So okay, this relation reflects the causal relationship. So, and another relation is the conflict relation, which should be symmetric and reflexive. In our case, this relation encodes mutually exclusive events. You can see that each of these reads are in conflict because none of them can occur simultaneously in the same execution of the program. Okay, now put it formally, event structure is a tuple with 3 components. So the first component is the set of events, E. Then we've got causal dependency relation, which should be a partial order, and with the property that every prefix should be finite. Okay, also we've got a binary conflict relation. It should be reflexive and symmetric, and also satisfies such property. If we've got 2 events, E1 and E2, and they are in conflict, and event 3 causally preceded by event E2, then event E1 and E3 should be in conflict too. So now let's talk about advantages of encoding semantics of concurrent programs using event structures. The first advantage is the compactness. Yes, we have seen that really in event structures we've got much less events than in interleaving semantics. Also completeness in that sense that with one event structure we can encode all executions of the program. Also, last but not the least, advantage is parametricity. So what do we mean by parametricity? To understand that, let's us consider another example. So given the following program, and the question is whether we can read here and here two zeros. And of course, answer depends on our semantics of concurrency, our memory model. In sequential consistency, the answer is no, yes, but in relaxed models, this behavior is allowed. So let's look how we can establish this result using event structure. First of all, we should build event structure corresponding to this program. Here it is. It's not very difficult. Yes, we first just write 0 to x and to y. Then we've got two different threads, yes, where we write 1 to x and y. And when it's done to read here, we've got two possibilities. We can read 0 and 1. So note that this event, this read, connected with this write, yes, because it just reads, this read just reads from this write. And of course, these two events should be in conflict, yes, because they can't occur in one execution of the program. So we are interested if these two events can occur in some execution, and to understand it, we should find some maximal subgraph of this graph that should be non-conflict and contain these two events. So here it is, and now it is suffices to check if this graph satisfies the memory model's consistency constraints. So event structures were introduced in 1980s. In recent years, there has been renewed interest in event structures with various applications. However, to best of our knowledge, there is no mechanization of classical theory of event structures in proof assistance. And we decided to close this gap and develop a mechanized theory using Coq proof assistant, especially use SSREC dialect. And now let's talk about our plans. So our plan is to implement various classes of event structures, prove their properties, and establish connection between them. So in particular, we want to develop prime event structures and stable event structures. Based on prime event structures, we want to develop operational semantics which construct event structure incrementally, yes, in step-by-step fashion. And based on stable event structures, we want to develop the notational semantic, which constructs the meaning of program compositionally, yes, following the syntax of the program. And now we've got operational semantic of simple register machine using prime event structures. So in general, we want to apply all these constructions to develop the semantics of other concurrent languages like PyCalculus and CCS and so on.
Yeah, now let's consider an example of usage of our theory of event structures, specifically for the construction of semantics of a parallel register machine. First, consider the syntax of a one-threaded of a program of a register machine. It's simply a sequence of instructions where each instruction can be an assignment to the register, a binary operation, conditional jump to a specific line of code, exit from a program, and read and write from or to shared memory. And the semantics for one thread of such a program can be defined using the labeled transition systems, And here P is a program, and S and S prime are thread states of a program, and they are defined by an instruction pointer and a map that maps registers to their values. And also these states can be connected with the labels, which can be an empty label or a write of a value to allocation or a read of a value from allocation. For example, if we had such a program in the left column, then we can construct some steps of the transition system. Here we have an initial thread state, then we write 1 to X, so we have such a label on this transition, and our register mapping doesn't change. Next, we read the value of X and write it to the register, so we have such a transition, and we update our register mapping with the value of R, and finally we can we step by the write label to the next thread state. And now let's consider an example of a multi-threaded program and construct its event structure. First, we initially have an event structure which consists of an initial event for each thread, which is named thread start. And next, we update these event structure step by step by processing our instructions. Well, let's first process the instruction from the first thread. Here we write 1 to X, so we add such an event to our event structure. Next, we connect this event with the event of with the thread start, because, well, this event simply cannot happen before the thread is started. And this relation is called program order relation. Next, we can similarly add the event for the third thread. And next, we have to process the middle instruction, which reads the value of X. And here we have 2 matching events for these reads. So we have to add two read events. And both of them will be connected with the start of the second thread by the program order relation. And also we introduce here a new relation which is called reads from, and it tells that a read reads from a specific write event. Yeah, well, here we are using a new, well, at least for here, relations called program order and reads from, but well, in classic event structures, the causality and the conflict relations are used. So we need to go from the PO and the ref to these relations, and it's constructed quite easily. For the causality relation, we just take the transitive closure of the program order and the reads from relation, and for the conflict relation, it's a bit trickier. We first look at the events that have a common program order predecessor. For example, here, these 2 reads have a predecessor, which is the second thread start. So these events are in conflict. And next, if these events had other ancestors, then these ancestors are also should be in conflict, but it's, well, for the next construction. Yeah.
Okay, now let's look at our future, not our nearest plans. So we are planning to implement stable event structures and develop with it the indentational semantic of register machine. So yes, this line, and then we will be able to connect our to our semantics and use them together. So I think that's all. Maybe any questions?
Thank you very much for your presentation. So questions, please. We have several minutes for questions.
Hello, my name is Irina Shushmina. I would like to ask, why do you call this approach as mechanical? What do you mean under mechanical? And is it something special? How do you think?
Yeah, well, I don't think they properly understood your question, but well, we mean parallel and
You
concurrent.
say that it's mechanized theory. I'm sorry, mechanized theory. Why is mechanized? What is mechanized here?
Oh, yeah, we mechanized this theory using a cock-proof assistant. So we formally defined these things and proved their properties formally again.
I see. Thank you. And what is about register machine? What sort of register? Are they safe? Are they regular? Are they atomic register? What sort of register do you model?
We just call. So we've got two types of variables. Yes. First type is the shared memory variables that are shared between different threads, and another type of elements that is that are for each thread. Yes, then this type of element we call registers. So
I see. Thank you.
So, some more questions?
I have a question.
Yeah.
So as far as I understand, you mechanized in Coq some theory about event structures. So my question is, what problems do you solve by that? Why is it important to define event structures in Coq? Is it like final step or it should be used for something? Why is it important?
I think we can, solve two goals. We can define a general theory of event structures, and so it would be possible to reuse this theory in another project, and also we can show how it can be used. So I think all of the things that you proposed can be solved in this way. So.
Sorry, but can you name some projects where it could be used?
For example, maybe, so Wikistamo, I heard that in this project event structures are used, so maybe if but there I heard we used some custom variant, yes, that is not obey all axioms. Maybe this theory of true event structures can help somewhere. And I think everywhere where you want to make semantics of some concurrent language, you can use this theory because it's rather general for it or something like that.
Thank you.
So, some more questions? Then maybe a short question from me. So just I would continue the question by Irina Shushmina. So just is your mechanized means operational semantics? It is the most standard thing, and I do not see the difference.
may I add, I think that is a sort of automated that should be used here. They mean that proof could be partly automated.
Then, so I think there are already enough, yes, standard words to express it.
Yes, there are some difference in notions that standardly used. It's better to read something before before introducing new notions.
Yes, and my second question, so just maybe, of course, you have this very specific problem, but you do not explain the context because there are different formalisms to express, to say true concurrency, and event structures is not the unique, and for many problems, so just it is not the best way, so just it should be explained somehow. And also when you start with this program for register machines, then so just it can be easily expressed with label transition systems. So just it looks like event structures are not really needed here. You lose concurrency when you translate it to label transition system. You can't implement it so just on several spreads, or maybe I haven't got it. But I'm sorry, we have. It was a long question. Maybe short answer if possible.
Yeah, well, there is quite bad sound, so we didn't get your question. Could you please repeat it a bit more?
Oh, so well.
I didn't catch your. Sorry, I didn't catch your question because of the sound.
I'm sorry, we do not have enough time, so maybe after the talk. Then, thank you very much. So I would like to thank the speakers and announce the next talk. That its title is Generation of Petri nets using Structural Property Preserving Transformation. It is a talk by Roman Nesterov and Semyon Savelyev, and Semyon Savelyev will present it, as I understand. So please.
Can you hear me?
Yes.
Okay, let me open my presentation. Здесь как ее развернуть? Спасибо. So thank you for all being here today. My name is Semyon Savelyev, and the purpose of my speech today is to present an approach to the generation of Petri nets exhibiting desired structural and behavioral properties. The work was carried out under the supervision of Roman Nesterov. So I have divided my presentation into 6 parts. The first 2 parts introduce the necessary concepts to understand. In part 3, we will talk about transformations and its application. Parts 4 and 5 contains the proposed approach to the generation of Petri nets and its experimental evaluation. So let's have a look at Petri nets. Petri nets are widely used to formally represent the behavioral or distributed systems for their precise semantics, which helps to prove many crucial behavioral properties, including boundedness, deadlock freeness, covering by place invariance, and others. So what Petri nets are formally? In general, it's directed by paired graph with two types of nodes: places, usually denoted by circles, and transitions, usually denoted by rectangles. The places of the Petri nets can contain tokens that can move along the Petri nets in accordance with the firing rule of transition. For example, for these Petri nets, you can see on the slide, there are no multiple arcs, and for the transition on the left of the buffer, this transition is active because each incoming place contains at least one tokens, and we can fire it. After firing, this transition consumes one token from each incoming place and puts it for each puts one token for each outgoing place. And so this animation don't work. I don't know why, sorry. But after consuming these two tokens, we will this transition will produce this token and like produce one token to buffer. After this, a consumer can take this token because we can represent incoming places in such Petri nets as conditions, and if there is a token in place, we can think of it like preconditions. All preconditions are sets, and after that, consumer can take this token. So let's talk about what is a process of model generation. For a given reference model, usually it's some simple model with known behavioral and structural properties. We generate its refinement. Refinement is a Petri net with more complicated internal structure. And we transform it stepwise, step by step. Each step is a transformation, which we use for some subnet of our initial net, or a net which we take from previous step. There are different approaches, and these tools are based on the different approaches. For example, process log generator or PLG2 generates process models too, but it's based on randomly generated context-free grammars and parameters such as maximum model size. Most of these tools, it's a P10 log generator, benchmark generator, BPMN process models, and of course there are different others, but these are the most popular. All of them produce correctness model, model corrected by their behavioral properties. So in modeled systems, for example, there shouldn't be any deadlocks. However, within our approach, a reference model may have, for instance, deadlocks, which will be preserved in its refinement. So, for example, we have such elementary net system. Elementary net systems is a fundamental class of Petri nets, where places can carry at most a single token, black dot. You can see it here and here. And in our study, we consider the generation only of elementary net systems. Usually such systems are using for model the control flow of distributed systems, while other aspects as data and time are not considered. Some of elementary net system are state decomposable, state machine decomposability. State machine sequence component is finite afternoon and a subnet of a Petri net is a sequential component if it's a state machine. It has only a single token in the initial marking. So our net elementary net system is coverable by sequential components if every place belongs at least one sequential component. In this case, we can split our initial Petri net into 3 different sequential components. The first one colored by blue, the second one by yellow, and the third one by light blue. I can say that state machine decomposable elementary net systems are free from contact when, for example, for any transition, both preconditions or places, incoming places have tokens, and post conditions, outgoing places have tokens, are free from this state. So let me continue with an alphamorphisms. A class of alphamorphisms has been introduced in a related paper. You can see in here, and it formalizes relations between an abstract elementary net systems and its refinement, where subnets in a refined model can substitute places in an abstract model. Using this example, we can briefly discuss the main intuition behind alphamorphisms. So alphamorphism is a totally surjective map from the set of nodes of a refined set, refined elementary net system, and one on the set of nodes of an abstract elementary system N2. So our refinement located here, and abstract one elementary system is here. So places in an abstract elementary net system can be refined with a cyclic subnet in its refinement. For example, this subnet refines only one place, P1, when this subnet of places refines place P2. An alphamorphism is defined in terms of how transitions in nets are mapped to nodes in its abstract one. If the image of transition in N1 is also a transition in N2, then their neighborhoods should correspond as well. And if the image of transition in N1 is a place in N2, then the image of its neighborhood in this place is this place as well. These constraints, combined with several other structural restrictions imposed on subnets in a refined elementary net system discussed in detail in related work, and assure the main motivation behind alphamorphisms. A refinement should behave in the similar way as an abstract model does. For instance, this elementary net system don't have any deadlocks. So these parts and these parts are in relation of alphamorphisms. Our refinement don't have any deadlocks too. So application of alphamorphism is a difficult one due to it's difficult there due to sophisticated strips for nets, and we apply to use step by step. As I said before, the direct application of alphamorphism is rather difficult for their sophisticated structural constraints. Our approach based on the subsequent application of local structural transformations comes to the aid of this problem. Every step of applying a transformation to an elementary net system induces a corresponding alphamorphism from a transformed model to an initial one. Moreover, after a series of transformations is applied to an elementary net system, there will be an alphamorphism from a result elementary system towards an initial one. And this simple scheme shows this. We have abstract one elementary net system. We apply several steps and takes its refinement. So refinement N2 and abstract or elementary net system N1 in relation of alphamorphism. So what is transformations? We can define transformation as rules. Every transformation have its left and right part. So it's changeable subset of subnet. And these subnet are what we should place instead of it. And there are different constraints on these parts. We used in our work 4 different transformations, and you can see them in slide. So first one is place duplication. We can duplicate place, creating new place P2 and copying every arcs from incident transitions. So in the same way, we can create a duplication of P1. We can duplicate it. The third one is transition introduction. We can introduce new transition for any place. And the fourth one is place split. We can split place with creating new place, and all outgoing arcs will be incident with the same set of transitions, and x1, xm, and y1, ym are subsets of set of transitions a1, ak. So as an example of usage of transformation appliance, you can see place 9, P9, and we applied for it a local transition introduction rule. And we take one step and we have a refined model. We have offered 2 algorithms that support the automated generation of elementary net system using the mentioned above structural transformations. The first algorithm corresponds to the generation of an elementary net system by applying a fixed sequence of refinement transformations to an initial model. We simply take a finite sequence.
Sorry, Semyon. So I'm afraid you do not have time to explain anything else. Could you shortly come to conclusions?
Okay.
So
there are 2 different algorithms. The first one is fixed generation algorithm, and it's simply applying of finite sequence of rules And the second one, here you can see the example of applying rule sequence P for initial pattern net and takes its refinement. The second one algorithm is randomized generation of elementary net system. So user can assign any probability of appliance for each rule and limit this or parameterize this algorithm with maximum size of nodes in elementary net system and assign max steps. And after that, in each step, we are looking for applicable transformations, normalize their probabilities, and select one of them and apply for our initial net. So these both algorithms are correct due to there is because first one is a finite.
I'm very sorry, but you take time from the
okay.
talk. You see, so just to summarize somehow.
Okay, we made an evaluation. We take different patterns and apply for them our rules. And you can see here the results of appliance. There you can see here you can see initial size of or amount of places and transitions and its information after refinement, how our net was changed. Here is an example of program realization. It's
yeah. Thank you.
And conclusion.
Conclusions, yes.
We can say that generation this approach based on applying transformation to a reference model whose structural and behavioral properties are preserved. And transformation extends internal structure of a reference model and do it more difficult one. And if initial model don't have any deadlocks, our refinement don't have it too. And we developed two fixed algorithms of fixed and randomized generations. So I think it's all.
Thank you very much. So I would like to thank the speaker, and so sorry we do not have time for questions, so maybe there will be some questions in the break or after the session. And our next talk is method of performance analysis of time critical application using DBNets by Anton Rygin and Sergei Shashakov, and Anton Rygin will present the talk. You're welcome, Anton.
So, do you see my screen? Do you hear me?
Yes, everything is fine.
Oh, can I start? Yeah.
Yeah. Sure.
Hello everyone. My name is Anton Rygin, and I want to tell you about the research that we have done together with my co-author Sergei Shashakov. This research is on developing a novel method of performance analysis for time-critical systems based on DBNet formalism. So let's start from problem we solve. There are some kind of systems, distributed systems, in that some large delay may cause to significant loss, financial loss, maybe some other loss. These systems require performance analysis, and in this talk I will call them time-critical applications. So some of time-critical applications, for example, some financial systems, they work as transactional systems, so they guarantee atomicity, consistency, and other transactional properties. And their logs often can be represented as relational tables. So existing solutions do not perfectly fit this case. We will see why this method more closely fits this case than other solutions. As I said, message of many transactional systems, not of all, but of many, they are represented as sets of tags and their values. So if we have tag value messages, we can represent logs with these messages as relational tables. Messages can be represented as table records or rows, tags as table attributes or just columns, and values as record attributes. I mean, concrete values in some in corresponding columns and rows. And so it means that we need some formalism that allows to model system control flow together with relational database states. And such formalism exists. It's DBNet. DBNet is a formalism that combines process model and modeling persistent data together. It consists of 3 layers. The upper layer is a control layer. It is a modified colored PatriNet. The middle layer is a data logic layer. It consists of sets of queries and actions for working with relational database, and the persistence layer is just a relational database. Here you can see example for of DBNet model for taxi booking systems. The upper part is control layer. It's modified colored PatriNet, as I said, and the bottom part, the lower part is persistence layer, is relational database schema. So in this work, we consider a fixed protocol, it is Financial Information Exchange Protocol, as a running example. I want to highlight it. It is just a running example. There are a lot of other transactional systems for which the proposed method can be used. The fixed protocol allows all trading parties to buy or sell securities in several milliseconds. And it means that any unspecified delay, milliseconds delay, yeah, it may cause to a large financial loss for a trader because the best price is missed and reputational problems for exchange. In the lower part of the slide, you can see the example of traditional fixed message. It is a traditional tag value message. It consists of tag values separated by a special character, delimiter character. The object of this research is developing a method for performance analysis of time-critical applications using DBNet formalism. Developing a software prototype for testing and demonstrating abilities of this method, and testing the method using the prototype and test data, which is, in our case, is a log of fixed protocol messages provided to us by a software developer for one of the global stock exchanges. Before I will start to describe the method, I want to introduce several definitions that we use in this description. So a request message, it is a message sent by the application, by time-critical application or its component. Response message is message received by this application in response to previously sent request message. Corresponding request message, it is corresponding request message for the given response message. It is a request message in response to that the given response message was sent. And similarly, the corresponding response message is response message for the given request message is response message sent in response to this given request message. And also we will call message pair. It is pair of request and response messages that are corresponding request and response messages for each other respectively. I will use a running example. It is it is a fixed. It is a DBNet model for fixed scenario of new order single. It is new order single message is used in fixed protocol for creating an order for buying or selling securities. The method consists of two parts: implementation requirements and set of steps for using the method. Let's start from set of steps for using the method. It is divided into 3 stages. The first stage is modeling a DBNet. We start from defining a scope of the modeled applications. It includes 2 parts. It is considered components of the application, which sends messages and receive responses to them, and considered message types, request and response message types. For example, if you're talking about the Sarang example, you can see message types that are considered in this example on the slide. So after this, it is necessary to make sure that the application works as transactional systems, and produce logs can be represented in form of relational database, as I mentioned earlier. Then we create a DBNet model itself. We start from persistence layer. It is the deepest layer. So we need to define a relational database schema, and in this schema, the table attributes will reflect text of considered request and response messages. For example, you can see on the slide from this rank example that we consider here a message type, client order ID. It is used in fixed for, it's used for identification of request message for creating order or canceling order, and sending timestamp. So after this, we need to create a data logic layer, model data logic layer. So insertion of the request message is modeled by actions with insert queries, DBNet actions with insert queries, and retrieving the request and the response messages is modeled by select queries in the DBNet. So you can see action for insertion of the new order single request message, and queries for retrieving all the messages in the example on the slide. And finally, in the DBNet model, we need to define a control layer. We need first to define system control flow, like in any PagerNet or DBNet. And after this, we need to assign actions with insert queries to transitions of the net in the control layer, and assign select queries to view places in the control layer. So for each transition that is connected with a view place which retrieves response messages, we need to specify a number of parameters as they are listed on the slide. They include maximum acceptable delay value. We will discuss it several slides later. Here you can see these parameters in the example. For example, here maximum acceptable delay value equals 100 milliseconds. So after this, the next stage is preprocessing the log. We need to make sure that all messages in this log are valid, and remove those that are not valid, and prepare the log in a format, file format, encoding, and so on, compatible with a software tool implementing the method. And finally, we can conduct an analysis. We just need to run a simulation of the DBNet model, and the performance analysis will be conducted automatically during the simulation, and we can analyze results after the end of the simulation when no transitions can be fired. Talking about implementation requirements for the software tool implementing the method. Firstly, DBNet general behavior must be implemented. After this, we need to support following rules. When a request message is inserted in an action assigned to DBNet transition, it should be stored in the memory, because we will need to retrieve this when we will retrieve the corresponding response message. And when a response message is retrieved by querying the DBNet, and so we need to execute the following sequence of steps for checking and delay in this message pair. So we need to retrieve the corresponding request message that was stored in the memory in the previous rule. Yeah. After this, we need to. So if there are no such stored corresponding request messages, then we just terminate this checking and delay and continue running of the DBNet simulation. If it exists, then we parse sending timestamps of both messages in this pair and calculate delay between them. If this delay violates the specified maximum acceptable delay, then the validation is considered failed. So you can see this example. We have two messages, request and response message here, creator is single and execution report. A delay between the sending timestamps is about 3 milliseconds. It is less than 100 milliseconds, then the validation is not failed. But for example, if the delay would be, for example, 103 milliseconds, it would exceed maximum acceptable delay and the validation would be failed. And two final rules. If there are several corresponding response messages for one request message, it is a valid case. We just need to consider only the first corresponding response message because we need to check delay before the first response to the request. And if the simulation is finished and it was not considered failed, then the validation is considered succeeded. So for testing and demonstrating method abilities, we have developed software prototype. It is a DBNet simulator. It's developed as a plugin for Renew. It is a Java-based reference net simulator. And also we have added the features for performance analysis as described in this method. Here you can see the UI of the prototype. If you're interested in this code, you can follow the link on the QR code. And so the prototype allows to model a DBNet, to conduct a performance analysis using the proposed method, and to work for testing this. We also supported this running example. Yeah, I mean fixed protocol messages. Yeah, also there was added feature that allows to work with a fixed log to a relational database interface like with database. Yeah. Here you can see the UML class diagram. It is not very readable in this scale, but we can see this part. So the main idea in this DBNet simulator, yeah, that we use those parts of Renew traditional Kubernetes implementations that we can reuse, and those that we cannot reuse, we just overwrite with our own DBNet implementation. For example, you can see that viewplace extends place, and so on. The same is for arcs and so on. Yeah. So also, as I said, the prototype allows to work with a fixed log. So alternative implementation of the database connection was created. All messages that are read from the file through this connection are stored in the memory. When the message is being retrieved through this connection, it's first searched in the memory. If it is not found in the memory, it is returned and removed from the memory. Otherwise, we scan the file until we will find this message, and we store all files, all scanned messages in the memory. This approach allows not only to scan each line of the file with fixed log only once, but also to limit the memory usage. And so talking about performance analysis, when the first maximum acceptable delay violation is detected in this prototype, info about this violation is shown and the corresponding CSV report is created. And all violations that are detected during the current simulation are written to this report. You can see the screenshot of the first message on the slide. The report contains all necessary information. It is message type, message ID, to identify this message, violated, so delay that violates the maximum acceptable delay and difference between this detected delay and maximum acceptable delay. This prototype was testing on the fixed log. So for two scenarios, new order single and order mass cancel request. And we also conducted the quantitative analysis. We calculated the counts of maximum acceptable delay violations for each value of maximum acceptable delay. For example, here you can see that for new order single request messages, all delays that are greater than 1 second, they are between 3 and 4 seconds. We also can see it here. And for example, we also can see that there are no delays in our logs for new order single messages greater than 7 seconds. It is an example of possible usage of this method, for example, using such quantitative analysis, and we will know how much ratio of messages violate each maximum acceptable delay value, and we can specify and adjust requirements or service level agreements, SLAs, based on this information. So to sum it up, we have developed a novel method of performance analysis based on the DBNet formalism. This method allows to apply already known approach that's used in relational database domain to a wide set of transactional systems. And I think the main advantage is that the method allows to combine the performance analysis with other approaches that can of verification validations that can be used with Petri nets, the modifications. For example, checking safety, liveness, fairness, and similar properties. And so we have developed a software prototype as a plugin for a new tool. We have checked it on a log with fixed messages. The conducted quantitative analysis of maximum acceptable delay violations demonstrate how the method can be applied for similar analysis. So the developed method can be used in the research in this domain as well as in testing real software systems. And future work possibly includes extending the method for use with hierarchical Petri nets. For testing more complex, maybe multi-agent systems. Extending the method for more complex variants of performance analysis of transactional systems. I mean, not only checking a delay, but something more complex, and developing more advanced and usable software tool, because now it is just a prototype. So here are references used in during preparing the article in this talk. And now that's all. Thank you for your attention. If you have any questions, I'm glad to answer.
Thank you very much. So since I forgot that we do not have the next speaker in the next session, so we have some time for questions now. Any questions? So if there are no questions, I understand that. So just it was a good presentation. So just everything is clear. Of course, the other possibilities, nothing is clear, but actually I consider it was well presented, and the topic is interesting, very practical, and uses some modern theoretical approach at the same time. Then, thank you.
Thank you.
Once more. So our session is over, and I just pass the flag to the next session, which will be in 15 minutes, I guess.